Uranium is a word that stirs curiosity and, at times, a sense of unease. We often hear it mentioned in relation to nuclear power, atomic weapons, and even science fiction tales involving radiation. But what exactly is uranium? To truly understand it, we need to look more closely at what this element is, how it was discovered, and why it holds such an important place in both energy production and human history. Uranium is a naturally occurring chemical element found on the periodic table with the symbol U and an atomic number of 92. This means every uranium atom contains 92 protons in its nucleus, making it one of the heaviest elements that occur naturally on Earth. If you were to hold a piece of pure uranium metal, you would notice its remarkable density. It is about 19 times heavier than an equal volume of water. This extreme density is one of the reasons uranium has such strong potential as an energy source. Let's explore this together here on History of Ordinary Wonders. The story of uranium's discovery is quite intriguing. It was first identified in 1789 by German chemist Martin Heinrich Klaproth while examining a mineral called pitchblende, now known as uraninite. He named the element after the planet Uranus, which had been discovered only a few years before. However, the true importance of uranium was not recognized until much later. Throughout most of the 19th century, uranium was mainly used to produce colorful glass and ceramics, as its compounds create a distinctive yellow-green fluorescence. At the time, people were completely unaware of its radioactive properties. This changed in 1896 when French physicist Henri Becquerel discovered that uranium salts emitted invisible rays capable of exposing photographic plates. This accidental discovery led to the study of radioactivity, later advanced by Marie and Pierre Curie. As a result, uranium's story became closely linked with the development of modern physics. From a chemical perspective, uranium is a silvery gray metal, but its true uniqueness lies in its nuclear behavior. Uranium atoms are unstable and can undergo radioactive decay. There are several isotopes of uranium, but the two most significant are uranium-238 and uranium-235. Isotopes are versions of the same element that share the same number of protons but differ in the number of neutrons. Uranium-238 accounts for about 99.3% of natural uranium, while uranium-235 makes up only around 0.7%. This small portion of U-235 is what makes uranium so valuable for nuclear energy, as it is fissile. This means U-235 can split when struck by a neutron, releasing a tremendous amount of energy. This process, known as nuclear fission, forms the basis of both nuclear reactors and nuclear weapons. The energy released from splitting a single uranium atom is incredibly small, but when billions or even trillions of atoms undergo fission simultaneously, the resulting energy is enormous. A small pellet of uranium fuel, roughly the size of a fingertip, can generate as much energy as burning an entire ton of coal. This is why uranium plays such a crucial role in today's energy systems. In nuclear power plants, uranium fuel rods are carefully arranged within reactors. As the atoms split, they produce heat, which is used to generate steam that spins turbines to produce electricity. This process allows nations to generate large amounts of power without relying on fossil fuels, making uranium a key factor in efforts to combat climate change. However, this source of energy also raises concerns, as it produces radioactive waste that must be managed safely for thousands of years. Beyond its peaceful uses, uranium also has a darker side. During the 1940s, as part of the Manhattan Project, scientists learned how to harness uranium's fission properties to create atomic weapons. The bomb dropped on Hiroshima in 1945, known as Little Boy, was powered by highly enriched uranium. Enrichment is the process of increasing the proportion of uranium-235, making it suitable for use in weapons or reactor fuel. This breakthrough permanently altered global politics and warfare, turning uranium into a symbol of immense destructive power. Since then, it has remained central to debates over nuclear weapons, energy policy, and global security. Mining and processing uranium is another essential part of its story. Uranium is found in minerals within the Earth's crust, with major deposits located in countries such as Canada, Australia, Kazakhstan, and Namibia. Extracting uranium involves mining the ore and refining it into a concentrated powder called yellowcake. From there, it can be converted into uranium dioxide for reactor use or enriched further if necessary. However, uranium mining comes with environmental risks, including water contamination and radiation exposure for workers, which is why strict safety measures are required. Despite these challenges, uranium continues to be extracted due to its vital role in nuclear technology. Health and safety are always important considerations when discussing uranium. In its natural form, uranium is only weakly radioactive and poses more of a chemical risk than a radiological one. Handling small amounts is not immediately dangerous, but inhaling uranium dust or prolonged exposure to high radiation levels from its decay products can be harmful. This is why strict regulations are enforced in industries that work with uranium. Another notable point is that depleted uranium, which remains after enrichment, has been used in military applications such as armor-piercing ammunition because of its high density. This has led to ongoing debates about its potential health effects in conflict zones. Uranium is far more than just another element on the periodic table. It represents both human achievement and the need for caution. A metal that has powered some of our greatest advancements while also contributing to our most serious threats. As the world continues searching for sustainable energy solutions, uranium will remain at the heart of the discussion, challenging us to balance innovation with responsibility. Thank you for watching. If you have ideas for our next video, feel free to share them in the comments below.